Welcome to this week's LLM's Research Podcast, where we are discussing research papers published from January 17th to 23rd, 2026.
And honestly, looking at the stack this week, it feels less like a collection of, separate papers and more like a manifesto for a completely new architecture.
It really does. I mean, usually when we sit down for these deep dives, we're looking at incremental gains, a slightly better benchmark, a faster tokenizer, that kind of thing. But the theme that's just screaming out from these papers is this idea of the action layer. It feels like we are finally crossing a bridge from models that just observe the world to models that actually, manipulate it.
That is the defining shift. For the last few years, the main paradigm in multimodal AI had been what you'd call passive perception.
Right.
Show a model a picture of a messy kitchen, and it says, I see a sponge and a dirty plate. Which is, impressive computer vision, sure, but it's fundamentally passive.
It's just a captioning machine. It's a spectator.
Exactly.
Yeah.
But this week, we're seeing this move to active control. Now, that same model looks at the kitchen and thinks, okay, the plate is dirty, the sponge is there, I need to generate the motor commands to pick up that sponge and scrub.
So it's treating the output not as text for a human to read, but as a control signal for a machine to execute.
Precisely. And that fundamentally changes the stakes. If a chatbot hallucinates a poem, it's funny, right?
Yeah, maybe it rhymes orange with door hinge or something. It's no big deal.
But if a robot arm hallucinates a trajectory while holding a knife, or an agent hallucinates a file path while deleting data, that is a lawsuit.
Or a hospital visit. And I guess that's why we have to structure this deep dive so carefully.
It is. We've got three main buckets to get through to really understand this shift. First, we have to talk about reliability. How do we stop these agents from spiraling into errors? Second, the interfaces, how they physically see and move in the world. And finally, the most philosophical bucket, the reasoning. There's a huge debate opening up about how these models should actually think.
And as always, we'll wrap up with the practical side, how you can actually use this stuff. So let's start with reliability. You flagged a paper on agentic uncertainty quantification, or AUQ. This tackles something called the spiral of hallucination.
Right.
Now, I've seen this in chatbots. They make one small mistake, and then they just bend reality to justify it.
It is the sunk cost fallacy for AI. When an agent is doing a long task, like writing a big piece of software, it relies on its own past outputs as context. If it makes a tiny error in step one,
that error becomes a fact in its memory.
Exactly. The error compounds, it explodes. And the AUQ paper argues that current models are just too confident in their own memory. Their solution is fascinating because it borrows directly from human psychology.
Oh, from Daniel Kahneman.
Thanks.
Thinking Fast as Hell.
That's the one, System 1 and System 2. They implemented a dual process architecture.
Okay, so System 1 is the fast, instinctive part.
Yep. Your standard autoregressive generation, the gut feeling of the model. But they introduced this mechanism where the model's uncertainty isn't just a passive number anymore. It's an active switch.
So if the uncertainty spikes too high?
It forcibly triggers System 2. So instead of just logging, I'm 60% sure, in a server log, the system uses that uncertainty as a trigger to say, stop, do not generate, reflect.
I see. It turns uncertainty from a diagnostic into a control mechanism. It forces the agent to pause and verify before it commits an error to memory.
It breaks the spiral before it even starts. The model essentially says, hang on, I don't know enough to continue. I need to think harder.
But that whole thing relies on the model knowing it's uncertain. And we know models love to be confidently wrong. There was another paper, right? Agentic confidence calibration.
Yes, and it points out that looking at a single output just isn't enough to catch these things. Most confidence checks are too local. They just look at the last sentence.
So what's the fit?
They introduce holistic trajectory calibration, or HTC. The idea is that you can't judge confidence in a vacuum. You have to look at the entire history of the task.
So you're looking at the macro dynamics, like reading the vibe of the conversation.
In a way, yeah. It analyzes the stability of the agent's reasoning over time. If the agent has been wobbling back and forth on an idea for 10 turns, even if the final sentence looks confident, the whole trajectory suggests it's high risk.
It's detecting the wobble before the crash. That's incredibly useful.
And this all ties into a broader survey paper we saw, from passive metric to active signal. The whole community is shifting on this. Uncertainty is becoming an input.
Meaning, if a model's not sure, it should do something about it.
Right. It shouldn't just guess. That signal should trigger tool use. I'm not sure, so I will Google it, or I will ask the human for help.
Self-awareness as a safety rail. Okay, let's take that safety rail and put it in the physical world. Because if we're talking about the action layer, we have to talk about robotics. And this Cosmos policy paper feels like a cheat code.
It really does. It's leveraging the fact that we've gotten incredibly good at generating video.
Yeah.
I mean, we have models that can hallucinate realistic physics, like Sora.
Right.
The researchers just asked, why can't we use that dreaming capability to control a robot?
So they're actually using a video generation model to drive a robotic arm.
Yes, a model called Cosmos Predict 2. But the genius is how they did it. They didn't change the architecture. They just taught the model that the next frame of a video could be, a latent frame that represents a motor command.
Yay. Okay, unpack latent frame.
Yeah.
How does a video frame become a robot movement?
Think of it this way. A video model predicts pixels. It predicts what the world will look like in a tenth of a second. Cosmos policy tricks the model. It says, here's the current state. The next frame isn't a picture of the arm moving. It's the movement itself.
So the model hallucinates the movement, but instead of pixels on a screen, that hallucination gets translated into voltage for the motors.
That's it. And because that video model has watched millions of hours of things falling and sliding and colliding, it has this intuitive grasp of physics.
You don't have to code gravity into the robot.
You get it for free. The video model already knows how things fall.
That is just so clever. But there is a catch with these vision-based robots, isn't there? This Bayesian VLA paper points out that the models can get a little lazy.
It's called information collapse. It's a massive problem. If you train a robot in a kitchen and there's a sponge on the table, 99% of the training data is pick up the sponge. So the robot just stops listening to your voice.
It takes a vision shortcut. Even if I say don't touch the sponge, it ignores the text because that visual cue is just so strong.
Correct. Bayesian VLA fixes this with a really smart mathematical trick. It uses a dual branch architecture. It calculates the probability of an action based on vision only. Then it calculates the probability based on vision plus language.
And it compares the two.
It essentially subtracts the first from the second. It asks, what am I doing differently because of the text? It forces the model to isolate the influence of the language command.
It's forcing the robot to justify its action based on what it heard, not just what it saw.
And it works. They saw an 11.3% improvement on tasks. Where the instructions contradicted the obvious visual cues, the robot actually listens.
Speaking of surprising behaviors, we have to talk about LLM in Sandbox. This one made me laugh because it feels like we're over-engineering these agents.
And this paper suggests we just need to let them loose.
Yeah.
It challenges that whole specialized agent narrative. They put a standard LLM inside a secure code sandbox, basically a virtual computer.
Okay.
They gave it university-level chemistry and physics problems. But here's the key. They didn't tell it to code.
They just gave it the problem straight.
Yep. Calculate the molecular weight of this or solve this equation. And the model, on its own, realized, I can't do this math in my head. So it opened the file system, wrote a Python script, executed it, and read the answer.
It MacGyvered a solution. It used the computer as a tool.
Spontaneously. It implies that agentic behavior might not need fancy new architectures. It might just be an emergent property of giving a smart model a safe place to play.
It's not about training it to be an agent. It's about allowing it to be one.
But before we get too excited, you brought up Progress LM. This is the wet blanket paper of the week.
Unfortunately, yes.
We have these incredible vision language models that can see a robot building a Lego tower and describe it perfectly. Red brick on blue brick. But this paper shows they are terrible at understanding time.
Meaning they don't know if they're finished.
They lack progress reasoning. They can't distinguish between I am 10% done and I am 90% done. And if you're building an autonomous agent, that is fatal. It might stop building the house before the roof is even on.
So we have the action part down, but the duration and completion is still broken. That's a major bottleneck.
It is. We've mastered the spatial dimension, understanding the image, but we're still struggling with the temporal one.
Okay, so reliability is a mixed bag. Let's move to section 3, efficiency. Because running all these agent loops is expensive, we have some papers trying to make the machine leaner.
The standout here has to be SamTalk, representing any mask with 2 words. That just sounds impossible.
Right. Image segmentation, cutting an object out of a background, usually requires these massive, heavy decoder heads on your model.
Very computationally expensive. But SamTalk claims to do this inside the LLM itself by compressing their entire pixel mask into just 2 discrete tokens.
How do you describe a complex shape like the outline of a cat in 2 tokens?
It's a learned compression. Think of it like hash code. The model learns that a specific two-token combination represents a specific region map. This means a standard LLM can do pixel-perfect editing just by predicting the next two words.
That unifies the architecture. You don't need a separate vision brain and text brain.
It simplifies the pipeline immensely. And speaking of speed, there's Hermes. If you're running a video agent that needs to react in real time, you're always fighting latency.
The buffering wheel of death.
Hermes attacks the memory bottleneck. It reorganizes the KV cache, the model's short-term memory, into a hierarchical structure. Keeps the critical, need-to-know frames instantly accessible, and compresses the rest.
And the result?
A 10 times improvement in time to first token. That is the difference between a robot lagging for 2 seconds and reacting instantly.
That's massive for deployment. And finally in this section, OpenVision 3. This one's about consolidation, right?
It is. It's about stopping the redundancy. Right now, most systems use one model to understand images, like CLI, and a totally different one to generate them, like Stable Diffusion.
Two giant brains running side by side.
OpenVision 3 introduces a single visual encoder that does both, one eye for seeing and for imagining. And it performs comparably. It's another step toward that universal transformer dream.
Okay, so we've covered the body and the speed. Now we have to talk about the brain. The reasoning section this week is hosting a heavyweight fight. Diffusion versus autoregression.
This is a deeply philosophical debate. We know autoregression left to right, one word at a time. It's logical, linear. Diffusion is how image generators work, refining the whole picture at once.
And the assumption has always been that diffusion should be better for thinking, right? Because human thought isn't linear. We jump around, we revise.
That was the hypothesis behind the paper, the flexibility trap. The researchers thought if they let the model generate thought tokens in any order it wanted, it would find better solutions.
Sounds intuitive. Give the model freedom.
But they were wrong. It turns out that flexibility is a trap. When the model can generate in any order, it tends to avoid the hard tokens. It bypasses the high uncertainty steps that are actually crucial to solving the problem.
It procrastinates.
In a way, yes. It collapses the solution space to the easy path. They found that by restricting the order, forcing linear thought, and using standard reinforcement learning, they got much better results. They hit 89.1% on the GSM-8K math benchmark.
So for logic and math, structure is better than freedom.
However, the counter-argument comes from Stable Diffcoder. They looked at coding. And for editing code, diffusion wins.
Which makes sense. When I'm coding, I don't write top to bottom like a novel. I tweak a function here, change a variable there. It's a nonlinear process.
Exactly. They use block diffusion, which lets the model edit chunks of code in parallel. It outperforms the linear models because code editing is inherently about structure, not narrative flow.
So the takeaway isn't that diffusion is bad, it's use the right tool for the job.
Diffusion is for editing, autoregression is for reasoning. But there's one last paper that kind of blows up this whole paradigm, learning to discover at test time.
TTT Discover. This is the one that kept you up at night.
It is. The standard definition of a model is you train it, you freeze it, you ship it. During the test, the model is static.
Right. It can't learn anything new during the exam.
TT Discover says, why not? This approach lets the model perform reinforcement learning on the specific test question while it's trying to solve it.
Wait, it updates its own weights for just that one problem?
It explores the problem space, gets internal feedback, and actually updates its parameters to optimize for that specific instance. It finds a singular optimal solution for the problem in front of it.
That is profound. It's moving from generalization to specialization on the fly.
And the results speak for themselves. It solved open problems in math and biology that frozen models couldn't touch. It suggests the future of deep research AI isn't just inference, it is test-time training.
It's like the difference between a student answering from memory versus a student working through the problem on a scratch pad, learning as they go.
Exactly. It completely blurs the line between training and inference.
So we have covered a massive amount of ground, from self-reflecting agents to robots that dream. For the developers and researchers listening, how do we operationalize this? What's the Monday morning takeaway?
Okay, let's break it down by use case because the wins are very specific.
Hit me.
If you're in the visual space building UI agents or editing tools, SamTalk is your immediate download. Doing region selection with just 2 tokens, that eliminates so much engineering overhead.
And for the roboticists who are tired of their robots crashing.
If your robots are brittle, you are likely suffering from information collapse. You need to read Bayesian VLA. And if you're feeling experimental, look at Cosmos policy for that video-to-action pipeline.
What about for people building the brains, the reasoning agents?
2 things. First, Stop trusting your agent's raw confidence score. Implement something like AUQ. Give your agent a system 2 to stop and reflect. Second, if you're hitting a wall on reasoning, read the flexibility trap. You might be trying to be too clever. Sometimes strict linear structure is what the model needs.
And for video streaming.
Hermes, absolutely. If you need low latency and you have limited GPU, the hierarchical KV cache is the way forward.
It's fascinating. We are really watching the stack mature from look what it can do to here's how we make it reliable, fast, and grounded.
That is the action layer. We are no longer just passively observing the AI. The AI is now actively observing and manipulating our world. It's a brave new world.
And a perfect place to pause for this week. If you want the full breakdown, the math, the code links for every paper we discussed, and you really should check out that TTT Discover architecture. It is mind-bending. You need to subscribe to the LLM's research newsletter.
It is completely free, and it's the single best way to track this explosion of research without drowning in the daily ArcXViv flood.
We'll be back next week with another sec. Thanks for listening.
Goodbye.